कॉपी करतो माझ्या स्लाइड्स.
फक्त लाल बटन प्रेस कर. इथे दिसणार.
So team, please join us here. You want to duplicate or extend? Let me do extend. Better. Okay, just a second. This is what slideshow. It's PPT only. No? Excellent. So, welcome everyone. I am Samir Dhurde, and it's a big joy to welcome you on this live stream, to all the people joining online, and all of you who are joining us here in person at the Inter-University Center for Astronomy and Astrophysics. It is an exciting day for all of us, not just us, but all of us across the country, and people are very excited that the Aditya-L1 mission, which is India's next step in space observations and launches, is going up today with the PSLV XL also being tested. So we have a special program lined up for you, in which we thought that we will get you to interact with the scientists and engineers and the team which has actually made a little part of the mission, little but very important part of the mission. And at IUCAA here in the Inter-University Center for Astronomy and Astrophysics. And they will be sharing with you some of the mission details and and fun stories also, maybe about how the science went. So with this, I hope you'll be all feeling inspired at the hard work of the team and get a glimpse of what it has been to make this mission into what it is over the last 10, 12 years of theory and practice and practical development which has happened. So let's welcome, with a big hand, let's welcome the SUIT team and the Solar Astrophysics team from IUCAA on stage. Please, for a moment, if you can all come in the spotlight. Right. So, yes, we are waiting with bated breath for about in an hour. We will have the launch sequence already started, and we'll be hoping that everything goes perfectly well, just like it went with Chandrayaan, and we'll have our Aditya mission on the way to space. So in the meanwhile, as we have here, a good set of slides and a nice presentation prepared by our team here. So I hand over the mic first to Megha, who will be then leading the rest of the event. Thank you so much. The stage is yours.
Good morning, everyone. Yes, we are all super excited to see this event. Aditya-L1 is getting launched today from Sriharikota at 11:50 a.m. So this is Aditya-L1 with all its payload sitting on the tip of PSLV C57. So it is ready at its launch station, Sriharikota. A lot of research institutes have brainstormed for this mission. So mainly ISRO will be sending our satellite into space, and it also has provided its laboratories for building these payloads. So along with that, Indian Institute of Astrophysics, this is situated in Bangalore. So this is this has built the primary instrument called VELC, Visible Emission Line Coronagraph. So the next is IUCAA, our institute, and we are very proud that we have built an instrument called SUIT, Solar Ultraviolet Imaging Telescope. So you will be hearing more about it from our friends. So along with that, Physical Research Laboratory, Udaipur Solar Observatory, Space Physics Laboratory, and ISRO's branches like UR Rao Space Satellite Center. These are the main institutes which have contributed to both science, design, and instrumentation. Along with that, for the science, we have ARIES, situated at Nainital, IISER Kolkata, IISER Pune, and IIT BHU, and many more institutes. So we will see in the upcoming sessions that how these institutes have contributed to the different science payloads of Aditya. So with this, our friend Lynn here, who is a junior research fellow at IUCAA, will be speaking about what do we know about our sun. Okay.
Thank you. Okay, so before we dive into learning about all the exciting science that's set to come from the Aditya-L1 mission and from the SUIT instrument and all the other instruments, let's take a step back to recap on what are the things that we have learned about our sun in the past couple of hundreds of years. So let's see, what do we know about the sun? So we know that the sun is a middle-aged star, it's a main sequence star. And what does that mean? So that means that sun is a star like countless other stars in the universe. And all stars in the universe fall somewhere in this diagram called the HR diagram. This is a plot of the temperature versus the brightness of all the stars. And stars fall somewhere on this diagram, and they travel in their respective trajectories. For example, the sun started life somewhere here, and it's going to trace this path that is shown here, we call the main sequence. And right now, it's somewhere here in the middle of its journey. So, from the perspective of someone on Earth, it is also the source of all energy and all activity on Earth. So, we know that the sun provides life and energy to all the activities that is happening on Earth, starting from photosynthesis, that is a source of all energy, and from the cycles of seasons and everything that sustain life and all activity on Earth. So what else do we know about the sun? So is the sun a solid orb, or does it have structure? So as you can see from this figure and from the model on stage here, that the sun is actually a hot ball of plasma that has structure. It has a very hot core, which is the source of the energy of the sun, in which nuclear fusion reactions happen, and the energy from the center is radiated until about 70% of the sun's radius. We have a zone called the radiative zone, where the heat transfer occurs mainly through radiation. After that, we have a convective zone, where we have convection being the major process that transfers heat. This is just like how you heat water on a pan, you boil water, and you get convective motions of the water, and the water starts to bubble up. So similarly, we have the hot plasma bubbling up in the convective region, and then we have a very thin region called the photosphere. And in fact, it is this portion from which we get the visible light of the sun, and which is what we can view without specialized equipment. However, after the photosphere, we go to the chromosphere, which are also thin regions of the sun's atmosphere, and then we have a transition region, and then we have this corona. So these are the different layers of the sun. But how did we come to know about all of these things? So it all started with Galileo, who was the first to start looking at the sun, or start looking at the skies, in fact, with a telescope. And he was interested in observing the sunspots, although not directly. He projected them to a screen and he made drawings of it. And what you see here is, in fact, an animation taken and made from his own drawings that is animated to create this picture. We can see that he also demonstrated that these blemishes on the sun are not any planets or anything in between, but these are actual physical structures of the sun. And what this suggests is that the sun does rotate, and it's also not a perfect sphere like how it was believed in the olden days. So these are this was a very huge discovery back then. And what comes out of it? So we already saw that the sun is not a solid body but a hot ball of plasma. And when this ball of plasma or a gas, when it rotates, it doesn't rotate like the Earth, which is a rigid body. So in fact, on Earth, all latitudes will rotate at the same rate, but on the sun we have a differential rotation in which the equator the regions of the equator would move the fastest, and you will get, as you go along to the north, here you can see that to the poles you see a very slow rotation. This is called the differential rotation of the sun. And although we know about the sun, we observed the sunspots, people really didn't know what the sunspots were. Until George Halley shed some light on it. What did he do? He, in fact, was observing the light coming from the sun very closely, and he observed that when light that is coming very near, that is coming from region of the sun, very close to a sunspot are observed, those showed spectral splitting called the Seaman effect, which some of you may be familiar with from school. So this effect, actually what it shows is that the intensity, there is a very high or intense magnetic field near the sunspots which is capable of producing this splitting. So putting all this together, what can we see? We can see that there is a differential rotation for the sun, and we see that there is magnetic field lines in the sun. So there are these magnetic field lines that are called poloidal lines that have this particular configuration, and if you take something that starts from this configuration, if it undergoes differential rotation, it twists and turns all these magnetic field lines, becoming complicated structures, and also when you combine it with the convection that is happening in the sun, it becomes very complex. And where the convection doesn't happen very effectively, you have these sunspots, and that is what we know about the sunspots now. But these sunspots also are not there all the time. They come in and they come out and they vanish at certain times. So if this is the sun viewed across many years like that. For example, you can see the sun, how it looked to someone in 1996, and it goes on. There are many years of observation here. And you can see this is how the sun has many phases, in fact. And these are the different phases of the sun, and this is related to what we know today as a solar cycle. So the solar cycle was in fact discovered by Heinrich Schwabe, who was a German astronomer. He, through his meticulous observations of about 17 years of sunspot data, came to the conclusion that the sunspots varied with a pattern. The number of sunspots, in fact, had a regular repeating pattern to it that had a period of 11 years. So this is called the solar cycle or the sunspot cycle. And this diagram here, which is called a butterfly diagram, is actually a representation of such a variation. So after that, we know after Galileo, Newton was the first person to find out that sunlight is in fact composed of colors. So he can be counted as a father of spectroscopy. So after that, Joseph von Fraunhofer closely inspected the solar spectrum to find that even the spectrum from the sun was not perfect. It had certain dark lines as shown here. These are now called Fraunhofer lines. And later on, we come to know that these these particular lines are actually a signature. These are a signature of things that are happening. This is the signature of the elements and the conditions that prevail in the sun, and these can provide a lot of information about what is happening in the sun. So it is not that the sun is only radiating in the visible light. We can see that the sun radiates like a black body, almost like a black body, and which has a surface temperature of 5,700 kelvins. So it also has its emission in various other regions of the electromagnetic spectrum, and that is why we need instruments like we have on Aditya. So we can see that it radiates across a very broad area on the electromagnetic spectrum. So so why do we need all this complicated equipment? Is that the sun, when viewed through different regions of the spectrum, look very different. So here you have a Dopplergram which shows the motion of the sun. You can see that the sun, which is brighter here and is darker here, which shows the velocity of the regions of the sun. We have magnetograms, which are a depiction of the magnetic field in the sun. We have the continuum line emissions. We have the sun as seen in various other filters. And you see that we are seeing the photosphere in all these areas. We are, in order to see the chromosphere, we need to, or the transition region, we need to use certain particular wavelengths. And this is how when the sun seen in that wavelength looks like. So you can see that the sun looks quite different in all these different wavelengths. And this is necessary for us to learn about the different dynamics happening in the sun. And that is why we need all of the things that we are sending right now in the Aditya-L1 mission. So with that, I will pass on this presentation to Megha itself, who will talk about why we need to study the sun.
Yeah, you now know that the sun exhibits differential rotation. Its different latitudes rotate at different periods, and the sun has magnetic fields, and this magnetic field is not constant, but it varies over a period of 11 years, which is called solar cycle. So based on when the magnetic fields are highest, lot of activities takes place on the sun. So around that time, why do we need to study the sun constantly to know these variations? Let me talk about it. So once again, we belong to the solar system. Sun is our star, and it's our nearest star. Because of its proximity, we can actually see highly resolved patterns of the sun. For example, here, so whatever is happening, this is the, you can think it as a photosphere of the sun. So you can see that these are the indications of the convection which is happening on the surface of the sun, where the hot blob of plasma is going up and down on the surface of the sun. So on top of it, the sun provides a unique laboratory to study, to learn about a lot of different branches of science. So by studying sun, you have to handle a lot of images, and you have to study the image processing, right? So with that, you will improve your computational science and data processing skills. So the sun has 8 planets. So by studying the different planets of the sun, you can learn about the exoplanets. That means the planets which are outside the solar system, like some other stars hosting the planets called exoplanets. So you can know about that. And by studying the sun, sun is typically a cool star. So you will know about similar stars in our galaxy or in our universe, how they behave, what is the type of activity going on in those type of stars, and the stellar structure of those stars. And also you will learn about fundamental physics. You know, Lynn just said that nuclear fusion is the main process which gives out the energy of the sun. So in this process, sun gives a lot of neutrinos. So by solar neutrino problem, which was called, and we got a Nobel Prize also for this. So these type of fundamental physics can be studied by studying the sun. And you know that the sun is made up of hot blob of plasma. Plasma means you have ions, charged particles, atoms, and molecules. So by studying the spectral lines formed on the sun, you can know about atomic and molecular physics. Many elements were actually found out by studying the solar spectra. And again, you will learn about plasma physics. And you know that sun again is magnetized, and you'll know about the turbulence and dynamo activities happening on the sun by studying the images of the sun. And also we belong to, again, a solar system, and sun constantly emits different types of radiations and particles. So we actually belong to sun's climate, so which is called space weather. So we need to study all these things to understand our sun, and also sun gives a laboratory to study the different branches of science. Again, most of the events happening on the sun are because of the magnetic fields present on the surface of the sun. So like you heard about the sunspots generally will have two different components, which are called umbra, where the magnetic fields are just coming out of the from below in vertical ways, and where the field lines become horizontal, you will call something it as penumbra. So wherever the field lines are strong, the magnetic field lines around these sunspots can carry the plasma of the sun higher up in the atmosphere. So such events can give rise to coronal loops, solar prominences, etc., in which the particles from the sun can reach away from the sun, are thrown out of the solar atmosphere, and also the part of interplanetary system where we live in. The magnetic field lines coming out of the sun can suddenly cross over each other, and they can get cancelled. So these are the places where we see sudden burst of energy coming out of the sun. So that is called solar flares. And when the solar flare can be imagined as a to very high extent, where large amount of energy and particles are being thrown out, they are called coronal mass ejection. So along with that, without any of these activities also, sun is constantly throwing out the charged particles towards the interplanetary space. So this is always there as a constant, but this solar wind can carry more number of particles when the events like solar flares and coronal mass ejections takes place. So it's very important to monitor the sun to check these constant variations that are occurring on the sun. So coming to the space weather, like I said, the particles thrown from the sun will reach towards all the planets which are situated in the solar system. So coming to the Earth, so Earth has its own magnetic field. It's usually a dipolar magnetic field, as you saw here. And when the particles come and hit this magnetic field, you see that the other side, which was symmetric before like this, will be thrown out, and the field lines become open. So this forms a part of something which you have studied called Van Allen belts. So the particles which are thrown out of the sun will interact with the magnetic fields of the Earth, and they spiral about these field lines, and they also interact with the atoms and molecules present in Earth's atmosphere, like for example oxygen and nitrogen atoms. So when such thing happen, so you can see these green lights or red lights, they are called northern or southern lights or aurora. So as beautiful as it sounds, it's very beautiful event, right? So it's beautiful as long as the particles coming from the sun are not so energetic enough, or they are not so dense enough. But when there is an event of CMEs or coronal mass ejection or flares, so you have a lot of energy being thrown out towards Earth. So these particles coming out can interrupt the satellites, the aviation, and also the power grids on the Earth. So you know that these many satellites are there around the Earth, revolving and giving lot of information regarding GPS, and lots of things which are happening on Earth are handled by these satellites which are going around the Earth. So maybe last year you had heard that 40 satellites of SpaceX was just, they worn out because of the solar flare, which they were not aware of. So these particles which are coming towards the Earth can change the orbit of the satellite in which it is assigned to be rotating. So the satellite can slowly spiral away from its orbit and can be lost from our hold. And also it can directly affect, like the satellites can go completely disrupted with the action of these particles. And also you can have a blackout on Earth, which had happened in 1850s. So at that time there was a very big flare and people were not aware of, but from last 150 years such events haven't occurred, but we have no guarantee that it doesn't take place. So we need to constantly monitor the sun. So with these science goals, these are the major science objectives of Aditya. So like Lynn said, the solar atmosphere's temperature keeps increasing towards the corona. So we are interested to learn about the coronal heating and the solar wind acceleration. How much is the speed, with what speed it is reaching Earth, etc. And to understand the initiation of coronal mass ejections, flares, and near the Earth space weather. And also to understand the coupling and dynamics of the solar atmosphere. Sun has chromosphere, transition region, corona. So how the energy from the photosphere is transported through these different layers and how it is going to reach the Earth is the main motive. So with this, let's now go to Aditya-L1 payload. Why it is called Aditya-L1? Because L1 is a place where we are going to launch it. So Biswanath here, who is Senior Research Fellow, he will be talking about where is Aditya-L1 heading to.
So, hello. So, you see Aditya is there and L1 is also there. So what is L1? So for that we need to consider three body problem. And here you can see that Earth is there, Sun at the middle, and a surface type is there, surface like there. So around Sun we can see a very big dip, and around Earth we can see slightly smaller dip. So these are this surface is called potential surface, and it's law of physics that any object tries to lower its potential energy. So any ball, any object, suppose at L1 you can see a if you put a ball on that surface, that ball either can stay there or roll down along the surface. So depending on that position, you can classify 5 points called, these are the 5 points, L1, L2, L3 and L4. You can see L1 point is there between Earth and Sun. Earth and Sun, and these points are not only there for Earth and Sun, but also for Jupiter and Sun. You can see some asteroids are there at point L4 and L5. So these asteroids are there at L3 and L4 are stable points. So that's how we would send Aditya-L1 to L1 point. That's where the L1 name came. So Aditya-L1, so this is the trajectory of ISRO, that satellite, that from Earth to L1 point. That L1 point would be around 1.5 million kilometers. That is 1% of distance between Earth and Sun. So L1 point is quite stable, and that will keep rotating with Sun like this way. Keep rotating with the axis between Earth and Sun. That's how L1 point. Now I would like to hand over to Deepak for further.
Okay, So I'll briefly introduce the Aditya-L1 science payloads. So we have Welk, Soot, Helios, Solex, Papa, ASPEX, and a magnetometer. So Aditya is a multi-wavelength spacecraft. That means that it has the ability to observe radiation in different wavelengths. So we have Welk, which will observe in infrared and visible, Soot, which will observe the sun in ultraviolet, Helios and Solex will observe the sun in X-ray. Then we have in situ payloads that will make measurements like Papa in electron and proton and ions, and magnetometer will just calculate the magnetic field at the L1 point. So we'll just study each payload individually. So starting with, we have Welk, that is the visible emission line coronagraph. So what is a coronagraph? A coronagraph is a device that is used to image the corona. So corona is the outermost layer of the sun. The thing is, the corona is 1,000,000 times fainter than the disk of the sun. So you cannot see corona with your naked eyes. So you need to find a way to block the light from the majority of the sun. So what we do is we put a disk over the sun, right? So we block the majority of light of the sun, and then only we can see the fainter corona. So that's what the Welk is going to do. Now, this is the Welk payload. So the Welk has the corona imaging capability with spectroscopy and spectropolarimetry. Our science goals are to observe corona and the dynamics and the origin of CMEs. So this is an image taken from one of the previous coronagraphs by NASA. So this is an image by LASCO C2 coronagraph. You see, this is the representation of the sun. So we covered the sun by a disk, and then we can see the fainter corona. So the explosion you're seeing right now is in coronal mass ejection. These are small-scale eruptions on the surface of the sun that ejects plasma and magnetic field. So you block the sun, and then you can see the fainter corona. The problem is, when you block the sun, you lose this data. This is sun, and you lose the data from here to here. So this is 1.5 solar radii, and this is sun. So the Welk is going to be looking in this region, which will enhance our understanding of this region. Moving on, we have SOOT, the Solar Ultraviolet Imaging Telescope. The SOOT has the capability to look into photosphere, chromosphere in narrowband and broadband filters. So, SOOT has 11 filters in near UV, which will use to look at the sun. This is the detector assembly of the SOOT, and this is an image from the IRIS spacecraft in magnesium-2 line, and we expect a similar result from the SOOT. Moving on, these are the principal investigators of SOOT, our very own Professor Durgesh Tripathi and Professor Ram Prakash. Yep. Next, we have the Solex, the Solar Low Energy X-ray Spectrometer, and Helios, the High Energy L1 Orbiting X-ray Spectrometer. So these two spectrometers are there to observe the X-rays. So they are mainly going to be used to study the flares. When you have a flare, you have a sudden burst of X-rays. So these two instruments will observe the X-rays, and they will send a trigger to the SOOT that yes, we have observed a flare. And then SOOT will be pointed towards the place where the flare is occurring, so we can see the flare in high resolution. Moving on, we have ASPEX, that is Aditya Solar Wind Particle Experiment. So, sun is not a quiet body, it's quite dynamical. So, there is a concept called solar wind. So, sun is constantly emitting particles in all directions, and that is what's known as solar wind. So, there are a lot of energetic particles in the solar wind. So, ASPEX is going to look at the composition of the solar wind, calculate the energy of the particle, their mass and velocity and all the other things. So ASPEX has further two components, the SWIS and the STEPS. The SWIS will be looking at the ions in the solar wind, while STEPS will be looking at the suprathermal particles. So if you remember the Maxwellian distribution, if you have a certain temperature, you can relate that temperature to a particular velocity. But the particle which have velocity greater than the Maxwell distribution will be called the suprathermal particles. So ASPEX has the capability of measurement of protons and alpha particles, and with this we need to we'll study the constitution of the solar wind and the energy distribution of particles in the solar wind. Finally, we have the plasma analyzer package for Aditya, Papa, and the magnetometer. So just like ASPEX, Papa is also an in situ payload, which will measure the constituents of the solar wind at the point L1. So Unlike ASPEX, the PAPA will measure particles such as electron and heavier ions. And again, it is designed to understand the composition of solar wind and perform mass analysis, so we'll know what kind of ions are there in solar wind, what is their energy, their trajectory, and all those things. Because, as we have already seen, the sun follows an 11-year solar cycle. What does that mean? So, our Earth has a period of 1 year. That means after 1 year, everything repeats on Earth. We come back to the same position, the seasons repeat, and we have summer again, we have winter again, all those things. So, similar to Earth, Sun has an 11-year period, meaning after 11 years, the Sun will go through the same cycle again. So, during this cycle, we have changes in the solar wind also. So, this will help track those changes. And lastly, we have the magnetometer, which will calculate magnetic field at the L1 point in all three directions, X, Y, and Z. This is the image of the Aditya, and this will be the magnetometer. So this is a 6-meter long broom on Aditya-L1. And we have 2 magnetometers, one at the end, that will be 6 meters away from the payload, and one in the middle, that will be 3 meters away from the payload. So with this, I hand over to Bhushan, who will explain suit in detail.
Hello friends, my name is Bhushan Joshi and I'm one of the team members of SUIT who actually use their own hands to assemble the payload and test it before sending it on Aditya-L1. You can see in the photo, this is our very first team which IUCAA, which was in IUCAA, and we started with this very basic schematic of what the SUIT payload would be. I would be talking on the SUIT payload, of course, because that's the one payload which IUCAA has made. So this is a very crude diagram which we made initially. Later that, our engineers who are now at abroad and studying in different universities, so they came up with the actual 3D diagram of how the telescope would look like according to the optics and mechanical components mounted on it. So this is again a very first representation of how SUIT was designed. In later stage, this was the actual diagram of what SUIT right now on Aditya-L1 is. This is a 2-dimensional diagram, and I quickly explain how the light would enter. So this is a flap, it's a door mechanism, so it's a closed door. Right now it is in a closed condition. So when it will reach to L1 point, we'll give command to open this door so that the sunlight will pass through it. So we have one first thermal filter here. So why the thermal filter is required? Because the sunlight is so powerful, I mean, it's so bright that will saturate our detector, means the camera, which is here. So we have almost 90% of light, more than 90% of light is transmitted back by this thermal filter, and the rest of light enters here on the primary mirror. The primary mirror is tilted. It's called off-axis Newtonian kind of telescope. So it's tilted mirror. So light will again reflected back on the secondary mirror, and then through a shutter vane, there is a shutter here. Through the shutter vane, we have 2 filter wells. So why filter is required? So I'm not going to go into much scientific detail into it, but just like if you want to separate some things, you use filters. So it's the same way. So the unwanted light, if you want to filter, we use these optical filters. So we have 16 such filters. There are 2 wheels by which we can make 11 combinations, different combinations. You can control the filter's location from Earth. So you can give command which filter you want in the optical path. And then we have this CCD, which actually I was worked on. These are the same, the previous, this is like a 2-dimensional representation. This is 3-dimensional representation of what SUIT is. It is just the covers on from all of the sides are removed to just see what is actually inside. So this is a journey, means I'm actually going 1 minute per year. So this is 10 years journey, and I'm covering everything. I have a lack of time, so I'm covering like 1 minute for 1 year. So the first few years were gone to make documentations. It's not that easy task to just think something and start building it, because there is a lot of other things involved. So after 2 years, we started getting actual components here at IUCAA. So this is first component which we received is a detector. The component which will give you the sun's image on Earth is this component. So this is engineering model, and that doesn't require much sophisticated handling environment. But still, we have one detector handling room at IUCAA, and we opened that here. Then we fixed this detector in one of IUCAA's cameras to just check whether that is working with our expectations. And this is called IDSAC. It's a IUCAA digital sampler array controllers, and many of my team members are working on this CCD controller from last 10 years. And we use this controller to read the first image from the suit detector here at IUCAA. So left side is the first image which we grabbed using our controller and suits detector. Then we assembled that in our camera, and we shipped it to ISRO for further testing with their electronics. After that, our FPGA team, means our electronic team, actually worked on the algorithm. You might have heard that we have some intelligence on board which will detect a solar flare and focus or capture that flare efficiently. So that algorithm is converted into programming language by my team members here at IUCAA. This is one of the examples I can give here is, so this is like, if you consider this is full image, which is coming from suit or from sun, and the flare is only on this green part. So instead of reading this complete image and later cropping it using some softwares, what we do is we crop it on the chip, means on the sensor we crop it, and we just read that much green part. So that saves time. So how it is useful in terms of a fast readout method, means we can read the flares faster than instead of reading it like complete image and then processing it later. So we have a lot of numbers. So these are some noise levels, and this is the first image taken at ISRO using their electronics. After almost 1 year later, we received these 2 boxes. Just don't underestimate by its look. It's the costliest component on the suit payload right now. Those are the flight grade detectors. And that needs extremely clean environment to open. And we don't have that here at IUCAA. That's why we took help from Bharat Electronics. We used their one of the clean rooms to open it and see everything is intact. Everyone can like estimate this era is like Corona era, because all are like wearing masks, and that's the time when we started getting all the mechanical components here. So here you can see one of the assemblies we are making on the table. This is the primary mirror, the first primary mirror received at IUCAA. This is a secondary mirror. I would like to share one more interesting detail about making a payload is, you can't make a payload and send it in a space. Like you cannot send the same hardware to the space. There are some certain stages. So at the first stage, you have to make a lab model. Means you have to prove your concept here at the laboratory. Then you have to make another model, which is called the qualification model, where ISRO performs all kind of physical and electrical tests. For example, they put everything in a vacuum chamber to simulate the space. They increase that temperature like are almost 100 degrees Celsius, and they reduce the temperature in like minus 100 to minus 150 degrees Celsius, and they vibrate so vigorously. It's like 10 to 12 G force they apply on each axis on your payload to see everything will be intact while you send your payload in a space. So this is from the lab model. I don't have any images from ISRO, and we are not actually allowed to have mobile phones or cameras while working at ISRO. So all the images are taken here in IUCAA's instrumentation lab. So this is the lab models, first primary and secondary mirror received during that time. So my teammates who work on optics, they aligned all the optics to prove that whatever we designed on the paper, on CAD, on computer, we simulated was actually giving the same result. This is the final DHA. DHA is the detector head assembly. So this part is a camera which is mounted at the very back side of the suit telescope, which will grab the image and convert it into electronics or digital format, and will send that on Earth. This is a lab model again. So to prove that everything is like fitting according to weight, according to size, according to physical and scientific parameters, we have to make this model. So this model is made here, and then we made a similar model. It's called qualification model, and this is a vacuum chamber. The good thing about this is also made in Pune. Means everything you can see here is means on this chamber, which actually simulates the space environment, is made in here, made in Pune. And then we shifted this complete chamber to Bangalore ISRO. You can see this is a final image. This is a flight model. We can call it as a FM of suit, but with covers. So to save our optics and electronics from radiation and the harsh temperatures, we put this MLI. So many people are asking me what the golden paper is. So it's called MLI. It's called multi-layer insulation, which saves a payload from harsh environment and like temperature and radiation. Now the suit is here somewhere, and this is complete Aditya-L1, which is now going inside a bigger chamber, which will simulate the space condition. You can compare with the human height, means how big the Aditya-L1 is. After successful testing, the Aditya-L1 is like kept in this chamber and transferred to Sriharikota. At Sriharikota, then it is encapsulated in, on a tip of rocket. It's PSLV C-57. You can see people are just pushing the tip around Aditya-L1. Then from the assembly building, it is transferred to an actual launch pad. So that is also a very tedious process. And you can see it's like a day and night process. It's like you can't keep rocket hanging in between the path. So this is again very sophisticated process. So now Aditya-L1 is here somewhere, and PSLV C-57 is ready to launch. So during this tenure, our team, which you have seen in my first photo, is increased, and now these are our team members who are behind it. Many of them are at Sriharikota to attain the launch, and many of you might have seen here on the stage. Thank you.
Hello. Thank you, everyone. Thank you, Aditya-L1 team. So we can have some questions, if you have any, for like 5 minutes, and then we can switch to ISRO's telecast. I request the team to please come on stage. All our team members can understand English, Hindi and Marathi. So there is no language barrier. You can use all these 3 languages.
Or you understood nothing?
We have a question here. We have a question.
Good morning to Aditya-L1 team. I wanted to ask that in 1850s we had a blackout on the earth because of the event which happened on the sun. Because we weren't able to detect it. But even if we detect it today, like if there is such an event today, how do we prevent a blackout? Thank you.
Okay, so you're referring to Carrington event in 1854. Yes? So during the Carrington event, there was a huge flare that caused insurge in the electrical lines. So that time, the only electrical devices that we had were telegraph lines. So the electrical surge was so severe that the electrical lines were on fire, and even the teleprompters, they got shocked. The thing is, now in the 21st century, we rely most on the semiconductor devices that operate on electricity. So if there was to occur a similar event, then there will be a global blackout. The thing is, you cannot avoid them. You cannot escape from the sun. The thing is, if you can forecast them that suppose you can predict that there is a solar flare incoming, you can just turn off your every equipment. Like, that's the only way to bypass them. You turn off all the equipments and let the surge go by, and then you can open them again. So that's the only way that I know.
My co-commentator, Shivika Swarnkar, who will be giving the commentary in Hindi. Copied.